So, hello everyone. My name is Christian Seifert. I'm from the Graz University of Technology and I'm in Austria. And I'm pleased to present our paper, which is now titled after a great suggestion by a reviewer, The Desire Methodology for Early Pre-Verification of Digital System Architectures via Estimation and Back-Annotation. The paper was researched and developed in collaboration with Christian Steger, also from Graz University of Technology, and Tiberio Fanti from NXP Semiconductors Austria. This work aims to pre-verify digital system architectures early on in the design process in order to minimize research and development effort during design space exploration. For this purpose, we established a methodology, and I'll guide you through how we approach the problem using composable nodes, trace-based estimation, and back-annotation. I'd like to start this presentation off with a bit of an explanation on what the problem we are trying to solve is and the motivation behind this work. In digital system development, late discoveries of architectural flaws are usually extremely costly. Often, system architects work with models that are either too abstract to predict real performance issues or register transfer level models, which, while accurate, come too late and with an immense modeling effort. In essence, we need early tools that can provide actionable feedback, which is ideally before RTL synthesis even starts early on in the exploration process. So the central challenge is that early stage models often have the problem of not reflecting the actual system's behavior. They are mostly static, non-adaptive, and sometimes disconnected from real-world metrics. Our aim is to create a dynamic estimation environment where models can be reused, adapted, and calibrated using empirical data, which enables more realistic architectural evaluation much earlier in the development process. In order to tackle these problems, we took a closer look at the V-model, which is a commonly used graphical representation of the design process. When looking at the V-model, it is visible that there is a gap between the design and the verification, which we wanted to bridge early on. As you can see here in blue, we added a pre-verification loop, which is in our case based on high-level estimation and trace-based back-annotation, which is implemented in our methodology. The back-annotation is supported by the dashed line, which connects communication logs into the pre-verification loop. These additions to the V-model let us validate key design decisions early, helping avoid the problem of working through the whole V-model only to discover a flaw late in the process, leading to a major rework later in the design process, resulting in immense losses of time and effort. In order to solve the aforementioned problems and introduce a methodology based on our adaptations of the V-model, we present DESIRE. DESIRE is short for Design Space Exploration System with Integrated Repurposable Elements, and it is an approach, or you might also call it a tool, that is supported by formal description, statistical log data, and visual feedback to provide early, close to realistic architectural evaluation. It is planned for DESIRE to be provided to the public as an open source tool as soon as the initial 1.0 version is stable, which as of right now looks to be between Q4 2025 and Q1 2026, and has a focus on reusability, reproducibility, and integration into standard workflows. So let's talk about what we want to achieve by introducing this methodology. DESIRE, the methodology, was built with a few key goals. First of all, we wanted to enable early performance insights. Secondly, we wanted to avoid the effort and burden of register transfer level modeling in the early stages. And further of all, to use already existing data in order to improve the realism of high-level models and therefore reuse parts of already established systems and solutions. All of this while supporting modular reuse across architectures. So overall, we want to combine the settings and boundaries of the specific use case and the architectural requirements in DESIRE in order to find good architectural solutions and avoids flaws and mistakes in the early architectural design process. Now that we've talked about the goals, let's talk about how we are trying to achieve them. The core concept of our approach are repurposable nodes. Any system component can be translated into a node with a certain degree of abstraction, with a few examples listed on this slide. These abstract units represent system elements like processors, memories, interconnects, but it's important to mention that they focus only on observable behavior, such as message handling, instruction invocation, or transaction latency. The idea behind a node is that it's configurable, reusable, and can be connected into arbitrary system topologies. The goal of the repurposable node was to keep them as simple and dynamic as possible, while also retaining their ability to represent a wide variety of components when adapted. So let's take a closer look at an example of a processor. In our abstracted node representation, this processor node consists of a message generator, a message handler, and buffers for the existing ports. This can also be seen here, like in this figure. And in this example, it's one with 4 ports. If we simply remove the message generator, we could easily represent a memory component, for example. So each node includes a varying amount of message ports, directional buffers, and a message handler. In order to estimate a system's behavior, various different nodes representing different system components and their according configurations are then interconnected with each other and estimated, mimicking the whole system. These structural elements let us simulate typical component behaviors to a certain degree, like memory access or communication, without the effort of simulating internal logic of the internal logic of each component. So in order to ensure formal semantics and tooling compatibility, we also decided on describing the base building blocks of the system behind desire in the architecture analysis and design language. So in order to do that, we defined generic nodes, various basic node types and their distinctions comparable to a basic library of components. Furthermore, the message structure, communication patterns, and generic operation sequences are defined to establish a common ground. As a short example, each node is defined as a process with formal properties, type, timing, ports, call sequences, etc. Over here we can see a listing, but this is just a short part of our formal definition, which can be found through a link in the paper. But there's the whole definition. The decision to formally define Desire's basic blocks supports the integration and compatibility with other tools and might provide a deeper insight into the workings of the tool for some developers. Now that we've talked about the formally defined basis of our methodology, let's talk about how the previously introduced generic nodes can be enhanced with empirically gathered data and where we align our estimation closer to real systems, even though it's on a higher abstraction level. In figure 4, we can see a graphical representation of how the back-annotation roughly works. On the top, we see an already implemented system component. This component might already be in use in a previous version, an RTL implementation of some sort, or in a system with a similar use case. In the bottom, we can see a node we try to back-annotate, and this is how the process looks like. First of all, we log the communication in a system for key components we want to estimate. In this case, this component. The logging is, like I already said, most effective when looking at systems that precede the new system or have a similar use case to it. For the loggings, we look into all of its connections to other components, which can be seen here in this graph. And we log the interactions of this component with all of the other components, or some of them, depending on what kind of setup you have then. These logs are then analyzed via our tool, and as a result we get statistical data for values like the instruction frequency, latency distributions, and instruction data. With this resulting data, we annotate nodes with statistical behavior derived from the execution traces and logs. So basically we feed the calculated data into the now back-annotated node, and the back-annotation dramatically improves the fidelity of high-level estimates, bringing them closer to its reference's behavior. Now that we've established the inner workings on the back-annotation process and defined what nodes are in our context, we can take a closer look at our methodology itself. For the tool's workflow, we start off with a high-level architecture consisting of system components. This architecture is then to be translated into a node representation, which can be seen exemplary in Figure 5, where you can see the system on the left side here and the node representation on the right side. Then we start off with defining the components which are necessary for the estimation. In the best case, there is already a previous version of the architecture which can be used to gather log data. This log data is then used in order to back-annotate system components. The more annotated system components there are, the closer the estimation will be to a real system. This is followed by building the node representation using the just defined system component nodes and interconnecting them as intended. Then the estimation is started, and the user is able to analyze the graphical and textual outputs to determine if their goals are met. Based on the results, the design choices can be tweaked or adapted until a satisfactory result is achieved, more or less in a loop, in a feedback loop, and this before having to put the time and effort into working with RTL code. So overall, our methodology represents a fast, low-effort, explore, evaluate, refine loop. In order to verify our methodology itself and compare various different layers of back-annotation, we decided to use a simplified NFC data reception use case as a proof of concept. A graphical representation of the use case can be seen in Figure 6, and it is built upon a minimal RISC-V based architecture consisting of a processor connected to a coprocessor and also connected to a memory via a bus. For this, we created a RTL implementation of the defined use case and simulated it. From this simulation, we collected logging data from various trace points, which can also be seen here. And we only focused on trace point 1 and 2 because we only wanted to analyze the processor when back-annotated. This logging data was then taken in order to back-annotate the processor system component. As like I said, this was the component we focused on. Also visible in the figure is that the processor has a variety of model variants, which we will talk about in a second. Furthermore, the figure also displays a sequential chart of the system components' interactions. The whole process starts off with the received NFC data being stored in the memory from an outside source antenna. This stored data is then requested by the processor and transmitted to it. The processor then analyzes the NFC data, and during this process, the coprocessor is interacted with in order to perform certain tasks with parts of the data. Ultimately, the data is stored back in the memory by the processor. Now that we've established how the proof of concept use case is structured and works internally, we can talk about the estimation and simulation results. I've already previously mentioned the different model variants, which we take a closer look at in the processor node. First of all, there's the base estimation, which has no back-annotation at all. and it simply generates and handles messages over a set amount of time, interacting more or less randomly with other suitable system components. Then there's back-annotation layer 1, which gives the node statistical data, like, for example, timing, instruction data, and which component is how likely to be interacted with. And then we wanted to go a step further and more closely resemble the system component by additionally incorporating the instruction call order into the back-annotated node, which is in our case called back-annotation layer 2. And finally, there is the RTL implementation, which acts as our baseline, which we compare against in order to determine a model variance suitability and to have something to evaluate against. When looking at the results of the different estimation approaches, which can be seen in figure 7 and 8, we can see that the base estimation gives a very rough estimation of the behavior of the system component. Back-annotation layer 1 gives a more or less randomized version of the system component's behavior, and back-annotation layer 2, on the other hand, closely resembles the behavior of the RTL implementation. The rough estimation of the base estimation can be explained with the component not having any back-annotation data and therefore interacting randomly with other system components. This is a feasible approach to estimate the system component's behavior on a higher abstraction level. Back-annotation layer 2 resembles the behavior of the system component too much and can be argued that it's overfitted to the RTL implementation system component. It is therefore rigid and not suitable for usage on architectures that vary too much from the system where the data was gathered. The more different the new architecture is, the less suitable is the overfitted back-annotation layer 2 to represent the system component. Back-annotation layer 1, on the other hand, is in a possible sweet spot of not overfitting to the system component in its specific use case, and also resembling the system component's behavior to a degree where it is closer to the RTL implementation without losing its flexibility of being used in similar or other architectures. It's important to mention that this system component also has some form of rigidity, but far less than back-annotation layer 2. So our key takeaways from the proof of concept results with the different back-annotation variants are that back-annotated nodes can resemble the behavior of system components and their timing effects more closely to reality. With this, the behavioral accuracy of nodes can be vastly improved, resulting in a system-wide improvement of the estimation. It's important to mention, though, that there's also the risk of overfitting, which we discussed before. So it was demonstrated with back-annotation layer 2, as the back-annotated node relied on too much information to stay adaptable and was not fit anymore to be used in architectures that are too different from the system the data for the back-annotation was gathered at. So it's all about choosing the right level of realism for a system based on the variance from the original system and the set exploration goals. Last of all, let's talk about the tool itself resulting from the methodology. In order to make this methodology accessible to the public, we have, as previously mentioned, decided to release the resulting tool as an open source solution to support developers while testing out various different architectures while keeping the effort as minimal as possible. So let's name a few features we added or we want to add or plan on adding to the tool in order to support users. We want to produce detailed visual and textual outputs for every system component representing a node in the system. There's also the aim for a system-wide heat map, component-level graphs, structured logs, and we're thinking about STL 2010 support. We also want to support reusable node libraries, making it easy to build and iterate quickly through various different architectures. Some features are already implemented while others are still being reworked or somewhere on a backlog. The plan is to release Desire as an open source tool between winter 2025 and spring 2026 on GitHub. And I hope I could pique your interest in this amazing tool we're working on. And if you're interested, please check it out. And if you're interested in working with it or on it, I'm always happy to help, and it will be possible upon open source release of version 1.0. So to summarize my presentation and reiterate on the most important points, we started off with why we are even interested in this topic and why we started working on this methodology, which is due to the costly results of early architectural design flaws or mistakes and the need to give an informed look ahead how a system might perform. This was followed by a look into how a simple adaptation of the V model might be able to fix this problem. Then the desire methodology was briefly introduced and followed by an explanation on how the most basic building blocks of it work and how they are structured. We talked very shortly about the formal definition of said building blocks in AADL. Furthermore, we talked about the back-annotation process itself, how data is gathered and fed into nodes in order to more closely align the nodes to real or more close to real systems. Then we talked about the workflow of desire and how our already existing architectural system can be estimated via this methodology. This was followed by a proof of concept implementation where we talked about this NFC data reception use case, how it's structured and its logic, and we talked about the results of various different back-annotation approaches where we discussed that overfitting might occur when too much information is back-annotated into the node, making the node inflexible and not suitable for representing other systems. And last of all, I shortly talked with you about the Desire tool itself and would be glad if at least some of you would check it out upon a release. Here I just wanted to quickly gather the most important references used for this work. And now that we've come to this slide, I wanted to thank you very much for your time and attention. And if there are any questions that came up during my presentation, please feel free to ask me now here in this call, or also via chat. If there's no time to answer your question, you come up with a question later on, or if it might be too detailed, I'm always looking forward to also receive a mail from you and answer it that way. In this case, you can find my email address at the bottom of this page. So thank you all very much. Thank you.